In this series of lectures, we shall attempt to solve nth order linear differential equation solutions. And we'll be using linear algebra, well, basically matrix methods. Now, first of all, what's a differential equation? Obviously, it's an equation involving derivatives, a function y and all possible derivatives. What does nth order mean? That means the highest derivative is an nth order derivative. Linear restricts us to only the first powers of the function and its derivatives, and there are no cross terms. So a very general linear differential equation, let us say fourth order, will be a function of x, then the fourth derivative, plus another function of x, third derivative, plus f2 of x, second derivative, plus f1 of x, first derivative, plus f0 of x itself, equals to an inhomogeneous term, q of x. Without loss of generality, we can always take the coefficient of the highest derivative to be 1. Then this is called the so-called standard form. Now, an equation like this can be written in matrix form. How? Since this is a fourth order linear differential equation, I'll have a four-dimensional column vector. I'll start with y, derivative, second derivative, and third derivative. I'll call this the y vector. Now, let me try to write this as d dx of this vector, y, y prime, y double prime, y triple prime, equals a matrix times the same vector, y, y prime, y double prime, y triple prime. Well, first, it's easy, because the top element is the derivative of y, y prime. So I see y prime here, so I should have 0, 1, 0, 0. The second one, derivative of y prime, y double prime. So I'll have 0, 0, 1, 0. The third element will be the third derivative, so 0, 0, 0, 1. Then the fourth derivative, of course, we should use the information from the differential equation itself. It's about time we do that. So the fourth derivative equals minus f0 times y, minus f1 times y prime, minus f2 times y double prime, and minus f3 times y triple prime. We are not done yet. We have the inhomogeneous term, 3 zeros and a q. So we can write this in shorthand, d dx y equals a matrix times y, and then the inhomogeneous term q. So the question is, what is y vector itself? Something about the solution. Solution is the case where no derivatives remain. All the derivatives are gone. Which means for an nth order differential equation, we should integrate n times. Therefore, we basically expect n arbitrary constants. Now, this is all nice and general, But to have a feeling, let us do some simple-minded solutions to get a feeling. Let me consider the simplest but non-trivial second-order linear differential equation with constant coefficients. Something like this: y double prime plus 5y prime plus 6y equals to 0. Homogeneous. And let me say x is on the positive semi-infinite x-axis. Now, rewriting the differential equation as d dx, it will be a simple two-dimensional column vector and a matrix, same thing. 0, 1 as usual, y is multiplied by minus 6 and y prime is multiplied by minus 5, if I take this to the other side. So this is d dx y equals a y, where A is a constant matrix. Now, whenever we have a situation where I have the derivative equals to derivative of something equals to that something multiplied by a constant, exponential comes to mind. So one might say y perhaps is exponential. But that doesn't make any sense because this is a vector and this is not. So let me multiply this with a constant vector v. So what will this become? The derivative of y with respect to x will be lambda e to the lambda x times v equals a times e to the lambda x v. E to the lambda x is never 0, so I can cancel both sides, and I have the familiar matrix times vector equals a constant times vector. This is the eigenvalue problem. Let's very quickly go over this thing. So minus lambda 1 minus 6 minus 5 minus lambda determinant equals to 0 gives us lambda square plus 5 lambda plus 6 equals to 0. So lambda equals to minus 2 and minus 3. And the corresponding eigenvectors, for example, subtracting minus 2 and putting minus 2 in here, plus 2, 2 and 1, to get 0, the eigenvector is 1 and minus 2. The one that corresponds to minus 3 is 1 and minus 3. So I have two different solutions. Let me say y equals, or perhaps that, e to the minus 2x minus 2e to the minus 2x, and e to the minus 3x minus 3e to the minus 3x. Something peculiar here. As expected, y vector is, remember, the solution and its derivatives. Same thing here, solution and its derivative. Yes, minus 2e to the minus 2x is the derivative of e to the minus 2x. Did I differentiate? No, I did not differentiate. I just did the eigenvalue problem, and the differentiation came out by some sort of miracle. Very quickly, let me come to the heart of the matter. As we are used to partitioning matrices, we can synthesize them, put them together. So I'll put these two solution vectors side by side. I'll call it the matrix F, and it will be e to the minus 2x minus 2 e to the minus 2x, e to the minus 3x minus 3 e to the minus 3x. This is the so-called fundamental matrix. And its name is not given in vain. It is truly fundamental. We will use this fundamental matrix in nearly everything. It is the key to the whole solution, homogeneous and otherwise. Now, let us not lose our perspective. The thing is actually much more complicated than a second-order linear differential equation with constant coefficients. In general, I have d dx y equals to a variable matrix times y plus an inhomogeneous term q. Now, p of x for a second-order linear differential equation will be 0, 1 minus f0 of x and minus f1 of x. But it can be nth order, and this may be larger matrix than 2 by 2. Now, how about solving this? Let us assume that there exists a solution which I will call the particular solution, d dx y sub q, I'll call this, is p times y q plus q vector in homogeneous term. So this is my solution. How I find it, I leave it to the next 10 minutes or so. But the thing is, if I have a so-called homogeneous solution, I'll talk about this in a moment, where y homogeneous satisfies the q equals to 0 case, and if I add them, I'll get d dx most general solution equals the P matrix times the sum of these, again the most general solution, and the inhomogeneous term. So the question is, if I already have a solution here, who needs this homogeneous solution? Why? Well, the thing is, the homogeneous solution, in this case, for example, is my fundamental matrix times an arbitrary constant vector c. You see, because it doesn't have an inhomogeneous term, I can multiply both sides from the right with a constant, arbitrary constant vector and regroup. So it will be also a solution. This will be necessary, these constants are necessary for us to fit the final solution into perhaps initial conditions, perhaps boundary conditions, whatever is necessary. Now, we actually had defined the fundamental matrix as a synthesis of the two solutions put side by side. So d dx fundamental matrix equals P of x fundamental matrix. So F satisfies the inhomogeneous differential equation. Therefore, a C here and here doesn't disturb the universe. So homogeneous solution is this. How about particular solution? For particular solution, we employ a method in which the particular solution is again the fundamental matrix times a variable vector z. Now this method is the so-called variation of parameters, which is not a great name. Actually, what we are doing is we are promoting a constant in the homogeneous solution to a variable vector and hope that this will work. So how do we go about this? Well, we substitute this particular solution into the original differential equation. So the first thing is to take a derivative. I'll have the derivative of f times z plus f times derivative of z. And this should equal to p times f z. Plus q, the inhomogeneous term. Now, since df dx equals to p times f, this term and that term very nicely cancel each other. And I have z or dz dx equals f inverse q, or z equals integral dx f inverse q. But it's not z that we really want. We want the particular solution, which is yq equals f of x integral dx f inverse of x q of x. Now I will manipulate this solution a little bit to give it a meaning, to relate it to things that we hear about. My first thing is to say, let me convert this integral into an integral not over x but x prime. So I put a prime here and I put an x here, meaning I will perform the integral over x prime, then my result I will evaluate at x, which is what I had a little while ago. Now I make a little bit of difference. This yq does not equal to that yq. I will say it is the fundamental matrix integral over x prime f of f inverse of x prime q of x prime. And my limits, now I'll say a to x. A is my initial point. Now, this is not exactly the solution I have here. In fact, here I have an extra term, this integral evaluated at a. So it is the fundamental matrix multiplied by a known constant vector. It doesn't make any difference because eventually we will add this to the fundamental matrix multiplied by an arbitrary constant vector. Arbitrary constant vector plus a known constant vector is again an arbitrary constant vector. Now, what's the use here? We do not like indefinite integrals. We like definite integrals. This is not actually a definite integral. This is an indefinite integral dressed as a definite integral. We will remedy that. But let me first say this is a of x dx prime, the fundamental matrix, inverse fundamental matrix as a function of x prime, and then the inhomogeneous term q of x prime. Again, this variable limit bothers me. So what do I do? If my total domain is a to b, I write this as integral a to b dx prime, fundamental matrix of x, inverse fundamental matrix of x prime, then u of x minus x prime. I'll explain this in a moment. The inhomogeneous vector q of x prime. Now, u of x prime, x minus x prime, is 1 if x is larger than x prime. It is 0 if x is less than x prime. It is the so-called unit step function. Now let us consider this integral a to b. I can think of it as two parts. First of all, a to x, which is the integral I have at the top, and then x to b. Now, x to b dx prime means x prime is larger than x. If x prime is larger than x, this kills the integrand, and I have 0. So I truly have a definite integral. Now, one defines at this point g of x prime as f of x, f inverse of x prime, u of x minus x prime. This is the so-called green matrix. And how about the most general solution? The most general solution will be y of x equals the fundamental matrix times an arbitrary constant vector c plus an integral over the whole range over the variable dx prime, g of x prime, q vector of x prime. Now, one word about this arbitrary constant c. If we are doing a realistic problem involving nature, so on and so forth, there is no place for arbitrariness. This c should somehow be evaluated using initial conditions, boundary conditions. Boundary conditions are actually much more difficult. Initial conditions are much simpler. So let me do that. Y equals fundamental matrix arbitrary constant plus. Now, of all these forms, I'll use this. F of x integral a to x dx prime f inverse of x prime q of x prime. Now, if I set x equals to a, y of a equals f of a c, then there is no contribution from here because the integral a to a is 0, which tells me that the arbitrary constant vector is f inverse of a times y of a. Therefore, y of x doing it here will be f of x, f inverse of a y of a plus integral a to b dx prime g of x prime q of x prime. Let's digress a little bit and talk about the unit step function. The unit step function is such a nice function. When we differentiate it, you see something like this. The derivative is 0 here, the derivative is 0 here, and there is a infinitesimal region of infinite slope, but the jump overall is 1. So this is nothing but the Dirac delta function. This we will need in a moment. Another thing I want to talk about is the fundamental matrix for the most general case would be a solution and its derivative, another solution and its derivative. So determinant of f is the so-called Wronskian. Now, this is a digression, but it helps. Here, it says if I know two solutions, then I may differentiate them, do this determinant, and get the Wronskian. But there is another shortcut method that helps us to get the Wronskian directly from differential equation. I think this is worth doing. Let's take the determinant y1, y1 prime, y2, y2 prime, and let us differentiate this, d dx. What is the derivative of a determinant? Well, we can differentiate row by row. Now, if I differentiate the first row, the result will be 0 because the first and the second rows will be the same. So it will be, the only contribution will be the first row staying intact, the second row being differentiated. But what is y1 double prime? It is minus f1 y1 prime minus f0 y1. Same thing here, minus f1 y2 prime minus f0 y2. But again, y1, y1, y2, y2, if I factor out the f0, it will give me 0 contribution. So nothing here. Now minus f1 I can take outside. So dw dx equals minus f1 times w, or Wronskian equals exponential minus integral f1 dx. So it is possible to just look at the differential equation, do this very simple procedure to get the Wronskian. Now, once you have the Wronskian and one of the solutions, then you can find the other solution. So let's demonstrate that a little bit. y1, y2 prime minus y2, y1 prime is Wronskian if I divide throughout by y1. This is a first order linear differential equation with a very simple result. And y2 will be y1 integral Wronskian over y1 square dx. This is the so-called Abel's formula. I'm doing this because eventually I'll try to give you an overview of the whole procedure. Now, these practical matters aside, let's do a little bit of formalism. A formal definition of Green's matrix would be for the ddx minus p y equals to q problem. The formal definition would be ddx minus p of x hitting on Green's matrix gives us the delta function times identity. Now, okay, this is a formal definition and it is also wishful thinking. If we can somehow find a Green's matrix that satisfies this, then everything is okay. How? I take this ddx minus p of x, g of x prime. I multiply this with the vector q of x prime. Same thing here, delta of x minus x prime, q of x prime. Then I integrate over x prime, over the whole range. Since this is an dx prime, p of x and the derivative with respect to x are untouched. Now, this is simply q of x, and which tells me that this is the particular solution. So, ddx minus p hitting on y equals q, the particular solution. Yes, but as I told you, this is very nice. It gives us confidence, but how to construct G? Well, this is how we construct G. Let us show that these two are compatible. Now, this definition I wouldn't call formal. This is a recipe. It's an operational definition. So I have here f of x, f inverse of x prime, u of x minus x prime equals delta, or should I say, does it equal to delta of x minus x prime times identity? Well, first ddx of these. So derivative of f times f inverse of x prime and u of x minus x prime. Derivative of first times second times third. Second does not contribute because it doesn't have any x in it. This one gives me just the delta function. So this is plus f of x f inverse of x prime delta of x minus x prime. That was the derivative. Now minus p of x fx f inverse of x prime u of x minus x prime. Does this equal to the delta function times identity? Well, df dx, remember, is p times f. So the first terms of both sides cancel. So at first I have a shock. They are not equal to each other, but no, they do. Why? When x equals to x prime, this is identity anyhow. When x does not equal to x prime, I have 0 equals to 0. So the formal definition and the recipe are not contradictory. Now this is all very nice, but is it practical? Let's make it more practical than it is. First of all, this y of x equals integral a to b dx prime g of x prime q vector of x prime contains too much information. Why? I'm not interested in this whole vector. Suppose I'm solving a fourth order linear differential equation. All I need is y. Y prime, I don't need to get it by matrix methods. I can simply differentiate y double prime, y triple prime, so on and so forth. So I actually want only y of x first element is needed. Another simplification is q of x is a very simple vector. It is 0, 0, 0, 0. Only its last bottom entry is non-zero. So q of x, let's say k, is the function q of x, the Kronecker delta kn. So let's do that. Y of x first component is actually a summation over k 1 to n dx integral dx prime g of x prime k1 and then q vector 1. Ters oldu. Tekrar editing. G of x prime 1k and then q vector k. Well, replacing this by the Kronecker delta kn, I get y of x equals, each Kronecker delta kills the summation sign, integral a to b dx prime, g of x prime, q of x prime. G of x prime is nothing but the Green's matrix 1n element, because k will be replaced by n due to this Kronecker delta. And this is the so-called Green's function. Now we are ready for an overview to summarize what we know and what we do not know. We start with our differential equation. We can, just by looking at the differential equation, observe the inhomogeneous term, no problem. Also, we can directly derive from the differential equation the Wronskian. Now, this is about all we can sort of automatically learn from the differential equation. Then at this point, we will have a hopeful assumption that eventually we will be able to find one solution. Somehow, how we do it is a question mark. To get the differential, to look at the differential equation and getting the Wronskian is, of course, Wronskian equals to exponential of minus integral f1 dx. Now it is possible, knowing the Wronskian and one solution, to get the second solution, y2. What happens if we have the two solutions? First of all, we can get these together and have Green's function. And or multiplying y1 by c1 and y2 by c2, we can get the homogeneous solution. Now, knowing the inhomogeneous part and the Green's function, this gives us the particular solution, and homogeneous solution and particular solution together gives us the final and most general solution. So it's a general view of the situation. Now, certain things are trivial, and only one is non-trivial. How to get just one solution of the differential equation, of the homogeneous differential equation, of course. So this is our most important topic that we will deal with. Another piece of wishful thinking is how nice it would be if I had an operator that took me from the initial point to an arbitrary point. If I know the fundamental matrix at the initial point f of a, and somehow I multiply this with the development operator dxa, that should give me f of x. D is development or evolution operator. Now, the trivial approach, d of xa equals f of x f inverse of a, is circular argument, because if I use f of x to get the development operator to find f of x, that does make sense. So Instead, we do an iterative approach and say there is a differential equation d dx minus p of x. Of course, if this satisfies f, then it also satisfies equals 0. But I can multiply this by f inverse of a. So d of xa would also satisfy. Now, my approach is I will assume p of x is composed of two parts, p0 of x plus p1 of x, and p0 is already solved. The results are well known. And I will assume that d of xa is d0 xa d1 xa. What are the properties of these development operators? From here, remember, it takes me from point A to point X. So if it doesn't take me anywhere, namely it takes me from alpha to alpha, I should have identity. How about the double product, alpha beta, d beta gamma? This should be d of alpha gamma. And using this setting, for example, gamma equals to alpha, you see that d of alpha beta inverse is d of beta alpha. These are typical properties of a development operator. So I'm ready to write this as d dx minus p0 of x minus p1 of x, hitting d0 of xa times d1 of xa, and to get 0. So the derivative of such a product, it will be derivative of the first times second plus first times derivative of second then minus p0 d0 minus p1 d0 d1 both take us from a to x. Now I told you that d0 is an already solved problem. So what is that? d dx minus p0 of d0 d1 is they are equal to each other. So these two terms cancel each other, and the derivative of d1 xa equals d0 inverse of xa, p1 of x. This combination d0, d1, let me write simply as d of xa. So I'm ready to integrate, but I will write this same equation, changing x into x prime. Differential of d1 x prime a equals dx prime. Then d0 inverse, well, that's d0 ax, then prime, p1 x prime, d of x prime a. And let us integrate from a to x. Well, the first term is obviously d1 xa. The second term, d1 of aa, which is identity, to be subtracted. But I'll write this to the other side as 1 plus a to x dx prime, d0 ax prime, p1 x prime, d of x prime a. But we are interested in d, which is d0 times d1, d of xa equals d0 xa plus, now d0 xa can easily enter an integral which is over x prime. d0 xa ax prime is d0 of x prime, then p1 of x prime, then d of x prime a. The limits are from a to x. I can take a look at this and see that it is very easily iterated, because d of xa involves d of x prime a. Let me write d of x prime a. So this will be d0 of x prime a plus a to x prime. But once I change my limit to x prime, it won't do to keep this as x prime. It's a dummy variable anyhow. dx double prime, d0 of x double prime, p1 of x double prime, d of x double prime a. Now, substituting this in here, what do I get? There is actually a much simpler way of approaching this problem, but that is for the next 10 minutes or so. So, d of xa equals d0 xa plus this integral. The first term comes first. Integral over x prime a to x, d0 x prime, p1 x prime, then d0 x prime a. Plus a much more complicated situation, integral a to x of dx prime, also integral a to x prime dx double prime. Now d0 x prime, p1 x prime, then d0 x prime x double prime, p1 x double prime and d x double prime a. What is the simpler diagrammatical method? Let us say d should be symbolized by a complicated line. And let us say d0 is simply a line. And let us say p1 is something like this. So what is this equation? It is a complicated line that takes us from a to x, which equals to the same thing, simple-minded, plus a to x prime is complicated, at x prime there is this p1 thing, and then from then on, from x prime to x, it is a nice straight line. Cheating from here, what's happening is I have ax equals ax plus ax, but there is this x prime, then a to x, then x double prime, x prime, and infinitely many terms. But okay, this is all very nice, but it leaves us with two questions. What are those two questions? I don't mean two questions for the whole of this iterative analysis. General. The first is how to get one solution. If we get one solution, we get the other solution by Abel's formula. When I have the two solutions, I have the fundamental matrix. If I have fundamental matrix, I have everything. The second question is how to break up P as P1